all the objects at the end of the Yeah, hi. Sorry, I got logged out, unfortunately. So yeah, am I audible? Guys, am I audible? Can someone respond? Yes, all right, okay. Moving ahead. Okay, yeah, I understand. So moving ahead, so we had discussed so far over here, right? So this greedy approach, and at the end, we got a label for it, everything, correct? So this is nothing but a regional CNN, like RCNN, right? Regions with CNN features. That's why it's called RCNN. Correct? Is this point clear? But then, since it's a greedy approach, and there are like so many patches that are going to be passed initially, and everything has to be passed through the CNN module, and then there would be a classifier, right? So this approach is very, very slow. So that is one major roadblock with this feature. So basically, this is nothing but the same block diagram that I was explaining. Like each patch is passed through the convolution network, and then there is, in this case, they have considered SVMs as the classifier. Then the B box region is nothing but the bounding box generator, right? If the component is there, then this yellow line you see, right? That is nothing but your bounding box. This bounding box generator will happen. So is this point clear? So there are certain challenges with RCN. So what are the challenges? Is like, since it is there are a lot of patches over there that we need to be classified initially. So it takes time, right? So it is not real time, right? And another thing is, since the patches are selected using selective search algorithm. So I hope we covered in our initial classes the difference between an algorithm and a model, right? Is everyone clear with the difference between what is an algorithm and what is a model? Yes or no? All right. Just ping your responses on the chat if you do not want to speak on the microphone. Yes, okay. It's clear for the leap. So it is a algorithm using which, so there is no learning happening. Selective search is an algorithm, right? And so it is also slow. So there are another variant that was proposed for CNN, RCN, like RCNN, it was called fast RCNN. So what was happening in fast RCNN is there is nothing new happening over here. Basically, the same approaches will be there, but it is just that instead of passing the entire regions, right, the entire image was passed onto a deep convolution network, right? and then there was a ROL projection happening. Okay. So can someone say what is ROL pooling layer? What will ROL pooling layer do? Any idea? Like basically ROI, sorry, not ROL, it's ROI pooling layer. Any idea? So basically what it is doing is it is reshaping the entire thing into a fixed size. And why do we need the image to be reshaped into a fixed size? Basically, this is some image. This is passed to convolution, but then there are different images which can have different sizes, correct? So, but then for our architecture to work, we should have an established layer size. Okay, we have some charts coming in. Okay. So for that thing to be established, there is ROL pooling layers. What ROL pooling layer is doing is nothing but taking the entire image when it's getting passed through it. So it's converting into a constant dimension such that it can be connected to fully connected layer, right? And once a fully connected layer is happening, then there is a softmax classifier sitting on top of it. So softmax classifier will do what? Any idea? We already discussed. Can someone say what will softmax do? It handle varied size images correctly because we prepare a neural network for fixed size and it cannot handle variable sized images. That's it. That's the reason why we need this ROL thing. Right. Okay. So now can you guys see why this algorithm is going to be faster than CNN? Like sorry, RCNN, the regular RCNN. Any ideas? Any ideas? Anything? Okay. So you see the major difference that is happening over here is instead of passing like all those segments, region proposals, we are passing the entire image at a time, right? An entire image at a time using the convolution feature map. So whatever feature maps seem to be closer to each other. So those chunks are taken and those chunks are passed through your ROL pooling layer. So that is nothing but that's how the subset of image is selected. Right. Once the image subset it took variable size, it can perform. It took variable size and it can perform on all subsamples at a time. No, it cannot take variable size, Ravi. Reason being that architecture is sequential, right? You have a fixed patch and then you have to pass it through a fully connected layer. Now your patch size can differ. That is true. So depending upon, let's say, if 70% is just the man and the horse, then it will the patch size for them will be bigger as compared to any other object. But then it has to be passed through a fully connected layer and the weights are going to be constant. Otherwise, what would happen is, for let's say you want to diversify the architecture and you want to have a different fully connected layer for all images. So what will happen is the forward pass will be different for all the images, right? And the backward pass again will be different for all the images. So it will not learn. So basically, you will have one layer for every image, correct? So basically, your architecture will not be generalizable. So is this point clear? Yes, okay. Okay. So that is the reason we go ahead with this ROL pooling layer and then softmax. So the thing is, it becomes a little fast as compared to the RCNN. Reason being that it does not have to look into the image patches at a time from the convolution map. Only it can pick up the image patches to solve the problem of getting different patch size. Right, we pass it through ROL pooling layer that converts all the patch size selected to a constant size, and then that is passed on to a softmax driven, like basically a fully MLP based classifier, a fully connected layer, after which there is a softmax setting. So this is nothing but your first RCNN. Is this point clear? Yes or no? Okay, if this point is clear, then we move ahead with faster RCNN. So the thing is, this algorithm fast RCNN is a little fast as compared to RCNN, but is still relatively slow because the way that proposals are still being selected is using the greedy algorithm, selective search approach, and greedy algorithms are by default slow. right? So faster RCNN proposes a different approach for selecting the region proposals in itself, right? Can someone guess what will that do? Any guesses? Chat, you can ping. So what will happen if the greedy algorithm is removed? Okay, see, I'll try to explain it using this block diagram itself. See, now in fast RCN, we saw that entire images passed through the convolution layer, it got feature map, and region proposal network was being selected using selective search algorithm. Now, in faster RCN, what they do is they train a separate network for identifying the proposal networks, correct? So what will happen is feature map will be that is separately trained. There is another architecture that they train, and once the feature map is passed through that architecture, it basically gives you the region proposal network in order of time t. Is everyone aware of the time complexity concepts, like order of n square, order of log n, and log n, all those things? Okay, yes. So basically, can you say what was the time complexity before when we are doing a greedy algorithm, and what will be the time complexity now, since we are doing it in a single step? Can someone explain that if you're aware of that concept? Okay, do think about it. The point is over here it will be in linear time, like order of n. Basically, because we have to select n patches, but it's not order of n because order of one itself. Reason being that a neural network, whatever it's getting fed to, it will give you the region proposals as an output as a single step, right? So a lot of time is saved. Now we do not have to go back and forth to identify all the region proposals, and then all those region proposals does not have to be condensed and does not have to be passed through your convolution neural network yet, sorry, classifier yet again, right? So with this, now what will happen is greedy algorithm is eliminated. Now in a single step, we get proposal network, region proposal network. Now again, the same thing concept has to be applied since each patch might be of different size. So ROL pooling is required, correct? So ROL pooling will be required for it still, such that all the patches become of the same size. Then again, the same architecture will be followed. Each of the ROL poolings output will be passed on to what? Can someone suggest? Uh, can someone ping what it will be passed on to? A fully connected layer. We saw here, right? We saw in this block diagram, see, RL pooling layer is passed to a fully connected layer. It gives a feature vector, and that is yet again passed to a MLP based classifier. This is nothing but an MLP based classifier. And parallelly, there is a bounding box regressor which gives you this lines, basically this yellow lines we saw right over here. So it gives where exactly these yellow lines that makes a boundary of the region. So that is nothing but given by the bounding box regressors. Let's not worry about it at the moment, but let's try to identify like how the algorithm works to identify the objects and the image. Okay, all right. So I hope this is clear. So this is faster RCNN, correct? Is this point clear? So this is just a comparison of the time speed. See, RCNN was taking 49 seconds for an image to be processed. And SPP net is yet another algorithm that is, we have not covered this. So it takes 4.3 seconds for object detection to happen in an image. Faster RCNN takes only 2.3 seconds. Fast RCNN takes only 2.3 seconds, and fast RCNN takes 0.2 seconds. Right. So you see that this is much faster as compared to the RCNN altogether. So hence it can be used for real-time object detection. However, if you look at it in faster RCNN as well, convolution is happening, right? So convolution is happening, meaning that the kernel has to skim through the entire image, and that will take some time. Is that point uh, justified? Like since it has to skim through the entire image, it takes a while to get that done. Is that point clear? Yes. So there was yet another algorithm called YOLO, like you only look once. that tried to handle that situation as well. It said that how can we make it even faster? So all those things that were slow has been addressed. Now the slowness is coming due to the CNN taking time to get the feature correct. So what it says is we need to look at the image only once. We did not skim through each the kernel every time. We just need to look at the image only once, and then we'll be able to identify the bounding box. So this is the concept based on which you only look once. YOLO is defined. So what it does is it does a S cross S grid on any input image, right? Basically, we saw that M cross M convolution was happening. So some similar to that S cross S grid is put on each image. Is that point clear? So is that point clear? Yes or no? Okay. Yes. Okay. This point is clear. All right then. So we got into an S cross S grid. So for each grid now, what will have? Any ideas? Any ideas? What will each grid contain? Now that the image has been divided into S cross S grid, what will each grid contain? Each grid will contain some patch of the image, yes or no? That's what I wanted as an answer, but okay. Some pixel values, yes. Some patch of the image. So that patch of the image. So what we do is we take each grid over here. So we take each grid over here from the image, and within each grid, what we do is we take M bounding boxes. Is everyone clear with what bounding box means? What bounding box means? Is everyone clear with it? Yes or no? See, bounding box was nothing but that yellow box that was surrounding the image region. We in RCN we saw that we passing that bounding boxes. Correct. A lot of bounding boxes for past images were being sent, and each of them were being classified like basically by the CNN network. So similar concept is employed over here. Within each pixel, we have M. Sorry, not pixel. Within each grid, we will have M what bounding boxes. Right. And now we have a class probability map. So this is nothing but a probability map. So let's say there is one thing selected and across which we have M bounding boxes. So this is M, basically this is class probability map for each of those M bounding boxes, correct? That has been identified. So now for any target label, so what we have to do, we have to find a probability that what is the probability that that particular bounding box contains that image, correct? So let's say there is an object A. So let's say there we have 5 objects in our image, right? In our data set, we have 5 objects. So across all 5 objects, we can generate this class probability map. Yes or no? For each of those grids that were passed, for each of those grids, we have M bounding boxes. For each of those M bounding boxes, we can have probability maps across for each of the target images, like whatever we have. And since one image is independent of the other, we can generate this probability map independently, parallelly. Is this point clear? Yes or no? So now that we have the probability map defined for each of the image using our training, during our training time, we learn a specific threshold. Like if the probability is higher than this particular threshold, there is a probability that this bounding box contains that particular image. Is that point clear? Yes, this point is also clear. Then once this point is clear, then would you agree if I said that whatever is, let's say the yellow regions are the regions that are the M grids that have values higher than the threshold. Then what does it mean? That this yellow patches contain that particular image. All of those M grids positively contain that image. Yes or no? Like that object in the image. Yes or no? Since all those yellow grids, let's say we ran it across the dog or the cycle. Let's say we ran it across the cycle, and this yellow, all this yellow M grids that are yellow, said that they have high probability values higher than the threshold that each of this grid contains a cycle's part or subpart or the entire cycle. Is that point clear? Then all this, since and all these point blocks are adjacent to each other, this point is clear. Okay. And since all these blocks are adjacent to each other, can we say that since they belong to the same object, we can just merge them to get final boundary of the object in the image? Yes or no? Can we do that? We can do that, right? And since all the images are independent of each other, can we do this parallelly across all probability maps? Yes or no? Yes, we can do this, right? Let's say this was done for object cycle. Also, parallelly, can we do the same for object dog? Because cycle and dog are not dependent on each other, correct? And for each of them, there is a threshold defined. Yes, is that correct? So if that happens, then parallelly we will have in single time step, can we get the bounding boxes for all the objects in our images? Yes or no? Can we get it? We can get it, right? So this saves our time that in CNN again we had to go through the entire image one by one, like kernel by kernel, we had to follow the strides. In this case, we do not have to do that. We just have to load the image once. So it saves further time, further some time as compared to the traditional CNN approach, and we call this YOLO model. So is this point clear till now? So this is how at the end we get the boundary of this thing. So and then YOLO is covered. So YOLO gives us the boundary for the image. Then yes, image object detection boundaries can be used for whatever downstream task you want to do. So far, are we clear so far? Yes. Okay. Yes. Okay, we are clear, right? All right. All right. So these are object detection algorithms. Now, so there are a lot more object detection algorithms, but these are some of the prominent ones. So basically, RCNNs were the basic ones, and YOLO started out to be state of the art. And there are a lot of variants of YOLO as well. I would suggest that you go ahead, but then this is the basic principle for all the YOLO algorithms. So I would suggest that you guys go through and skim through all of those YOLO algorithms, right? And then you can use anyone you want to implement for your object detection task. We have a project for object detection, correct? Yes or no? So this is how you can go ahead and detect the object. And let's say if you want to detect an object in a video, what will you do? So let's say video can be looked at, can we look the video as a sequence of images frame by frame, right? So for each image, now you do how to find the object detection. So for each of the frame of the videos, we can do object detection, and we just have to link them. The positional points in the vectors have to be linked in the across all the images, and then we'll get a trajectory across the video for that particular object moving. So this is how you can do a moving object detection. Correct? All right. So far, are we good? Are there any doubts till this point? Okay, if there are no points, then I would suggest that by you guys start working on your projects, because these are most of the concepts that we wanted to cover. And once your projects are done, then if you guys are comfortable and time permits, we'll go ahead with some advanced concepts, right? But then this is the agenda that we have covered so far. We have covered the classifier models. We have talked about how CNN extracts features. We have talked about object boundary detection. And what else did we talk about in previous classes? Can anyone summarize what all have we discussed so far? Nothing. All right then. So this is pretty much it. I presume there are no doubts. If there are any doubts, please ask within the next 1 minute, 2 minute window. Please ping it on the chat if you are feeling shy to talk. And otherwise, we'll close the session for the day. So I would suggest that these algorithms are not so simple to implement. Spend some time on it. Try to understand the mathematics behind it if you are interested. And then, yeah, we'll see you in the next class. Thank you guys. Thank you for joining. I hope you have a great day ahead.